Good afternoon, everybody. Thank you for coming this afternoon. This is a talk that is a Provost lecture and also sponsored by another lecture series, of which this is the third lecture. This is a series we put together through ETBI, which is an initiative at the university to develop sustainable technologies in energy, water, and information for remote off-grid communities. And the purpose of our lecture series has been to bring together a fairly diverse group of people who might not seem at first connected to that mission. There's certainly wouldn't call New York City a remote off-grid community, but we've had a wonderful day of trading information and contacts and so on with today's speaker, who will talk to you on that subject. I just wanted to let you know that TBI is still alive and well, and this is our third lecture, and we will be continuing with lectures on related subjects next academic year as well. So stay tuned for more like this, pretty eclectic, very interesting, good speakers. Don't forget. Okay, with that, I'd like to introduce a man who needs no introduction on this campus, the Provost, Dennis Asanis, who will introduce today's speaker.
First, I would like to say good afternoon to everybody, and I want to thank Dr. Harrison for his great help and vision to start this lecture series as part of the broader Provostial lecture series with the focus on energy and sustainability issues. We've had some great speakers, and today obviously is no exception to that. So we're really delighted to have with us Dr. Steve Koonin, who is now a professor at New York University, NYU, and he's leading there the Center for Urban Science and Progress, which he has formed. So it's really his vision that he will share with us today, and he'll give a talk entitled Adventures in Urban Informatics. Let me just say a few words about Steve Koonin, who I've known for quite some time now. First of all, a lot of you will be very excited to know that he's a professor of theoretical physics. And you know that here with the Young Institute for Theoretical Physics and all the other great work that we have, the Simon Center and everything else, this is something very dear to our hearts. He was a professor at Caltech, and he moved on from that to do great things in academic administration, including holding the post of provost. So we share a lot in common, although we did it at different times, maybe, or for that matter, different decades. Nonetheless, I think the issues are identical. You know, academic excellence and then finding budget somewhere to support your aspirations, and the budget is always less than your aspirations. You know, some things never change. Yes. So from that on, I would say Steve had the most interesting and exciting career. He went on to British Petroleum as their chief scientist, and you were in Europe, right, for quite some time. How many years? 5 years. And after that, another interesting turn, you know, he spent time as Undersecretary for Science in the Department of Energy. In fact, under that role, we interacted quite a bit with Steve when I was in my previous life at the University of Michigan, leading their Energy Institute and doing things as director of the transportation activities. So it's all exciting. He's also spent time in the Institute for Defense Analyses. So very, very interesting cadre of activities in the Department of Energy, the National Science Foundation, the Department of Defense. What he's been doing at NYU, you're going to hear about in a second here, but I'll just preface by saying this, as we're talking about it earlier today, this is now the time where we have to work on new challenges that we're facing in the mega cities of the world. We're going to be, some 9 billion people in just a little bit, and 70% of those basically live in these big cities like New York City. So there's no better test bed than New York. If you can win in New York, you can win anywhere. And so basically, in this age now where we're rapidly moving to behavioral sciences and linking those with data analysis, informatics, sensors, and so on, it'd be amazing to hear from Steve how to link up buildings and people and transportation infrastructure and sensors and sewers and roads and everything else. So with this, let's welcome. Thank you, Dennis.
So a pleasure to reconnect with you in different lives and many other friends that I've known over the years. As Dennis said, I want to talk about urban informatics in the context of this center that we are starting now about 3 years at NYU. We were announced as part of the New York City Applied Sciences competition just about 3 years ago. This was the announcement photo. Let's see, do we have a laser pointer? Yeah, there it is. I had the good sense to stand in the back because I had no idea what we were going to do. And everybody else talked about the real estate that's involved, okay, but just typical New York City. But we've come, I think, a long way in 3 years, and I want to tell you a little bit about the substance of what the center is doing and then a little bit about the center itself. So we're at the confluence of two big but simple ideas. The first is that big cities are important. The world is urbanizing rapidly. Right now, more than half of the world lives in urban areas, and by the middle of the century, it'll hit something like 75%. So cities are where the people are. They're where society happens, consumption happens, innovation happens. They will determine sustainability trajectories for the globe as a whole. As Jeff West likes to say, Jeff is another theoretical physicist who's gone bad into cities. He's at the Santa Fe Institute. Cities are both the source of our problems, but also where those problems will be solved over the next several decades. All cities have to be good for global reasons of sustainability, but any individual city needs to be as good as it can be for reasons of competition, for talent, capital, ideas. And being good means quality of life. It means efficiency of the city government. It means resilience, sustainability, citizen equity, citizen engagement. The other big theme is big data. The world is getting very good at sensing, analyzing, storing, transmitting data. This curve, which is already about a year or two old, shows internet traffic growing at 30% a year compounded. There are now twice as many devices on the net as there are people on the planet, and that's going up even faster. We're seeing a proliferation of static and mobile sensors. Things are getting connected to the net. And so I came out of the Department of Energy at the end of 2011 with a couple months to ponder what I was going to do, and decided that I was going to go instrument a city in the way that a scientist would think about the problem. And what you realize is that you want to know about 3 different dimensions of a city. You want to know about the built infrastructure, the grid, roads, not only the conditions of that, where are the potholes, but also the operations. Is the grid balanced or not? The second bucket is the environment, obviously meteorology, pollution, but also noise. Flora and fauna make up that particular bucket. And then finally, most interestingly, but also most problematically, you want to know about the people. Their location, their interactions, economic, communications, nutrition, health, and so on. Suddenly you realize you're deep into privacy issues. You can't study cities without studying the people. And we'll have more to say about privacy and what we're doing about that in a minute. But the underlying thesis of what we're trying to do is that if we can properly acquire, integrate, and analyze data in these dimensions, we can make city government more efficient. Better operations, better policy, better planning. We can help with citizen engagement and governance by connecting people better with their city. We can help the private sector develop new services for people and for corporations. Where do I site a retail store optimally? How do I stratify risk in an insurance company? How do I target resources in a political campaign? And then finally, we think that we can help a revolution in the social sciences whereby instead of doing controlled experiments in a lab or a survey of 10,000 people, you can suck up data on 500,000 people at once and use that to try to understand how people behave. So let me talk a little bit about urban data first before I go through a sampler of the kinds of things we're concerned with. Urban data have been collected for millennia. The word statistics comes from the Latin word meaning of the state, since the Romans needed to know what was going on in the cities of their empire in order to better manage it. Urban data have been plagued by being sparse and being episodic, and at least for a physical scientist, it's been very difficult to measure the system systematically and so test hypotheses. But what makes it interesting, let's say over the last decade, is new data technologies for acquiring, integrating, and analyzing the data make this a particularly interesting subject right now. I'm of the physical sciences background, as you heard, and I firmly subscribe to what Lord Kelvin said about 140 years ago or so, 30 years ago. If you can't measure it, you can't understand it. And you really need to do things quantitatively, and we're trying to bring a very quantitative orientation to this understanding of cities, as you will see. So where do we get our data from? What's out there that we can use to understand the city? The first is to realize that the city generates organic data flows, permits, fines, census data, just all by itself that you need to tap into. There's transactional data in principle, credit cards, phone records. There's operational data, traffic, transit, the health system, the educational system. And then more recently, there's modern data like social media, Twitter feeds, and so on. Then there's a proliferation of sensors. We all carry around sensors in our pocket. No doubt there are sensors in this room that sense the light, the temperature, maybe even the occupancy. We have portal sensors, toll booths, entrances to buildings, and so on. And then finally, for scientists, there are opportunities for novel sensor technologies, which I will show you several as we go through the next bits of the talk. Let me start with a simple one, records data. New York City in 2009 passed Local Law 84 that mandated that all buildings above 50,000 square feet self-report their annual energy usage: electricity, heating oil, natural gas, steam. Konstantin Contacosta, who's our deputy at CUSP, has been the principal analyst of this data for the last 3 years. I show you here a histogram for office buildings, about 1,100 office buildings in New York City, of the normalized source energy use intensity. In other words, how many kilobTUs per square foot per year does the building use? And you can see it's a distribution with quite a bit of a tail. Some buildings using as much as 5 or 6 times the energy of other buildings. One can ask, is that due to the construction of the building, its operation, the kind of activities that go on in there, or misreporting? Having such a large data set lets you go in with confidence to understand what the outliers are. If you look at residential buildings, i.e. apartment buildings, this is some 7,000, 7,500 of them. It's a more unimodal, simple distribution, but in fact still with a tail. It's interesting to understand that. One can go through and then start to stratify the data according to, for example, the year in which the building was built. If you just pay attention to the office buildings, you can see that the older buildings are more energy efficient, or at least use less energy per square foot than the newer buildings. Whether that's due to activity or glass curtain walls, which are notoriously energy inefficient, remains to be seen. Let me switch to a different way of looking at the city: cell phone data. Mr. Snowden, now about 1.5 years ago, famously taught everybody that CDRs exist, call detail records. So the phone company knows which tower a given handset is talking to at any given time. And before they closed up on that data, which is about the last 1.5 years, researchers could get hold of that. Marta Gonzalez at MIT and a bunch of collaborators got hold of about 6 weeks of such data in the Bay Area and Boston. And this particular analysis is the morning rush hour in the Bay Area. And they simply asked, on a given road, where did that cell phone come from? And there are about 500,000 cell phones in this data set. And so you could conclude, for example, in Hamilton Ave in San Jose, it came from 51 different cell tower areas. Whereas Hickey Boulevard up in Daly City, there were only 12. And if you're the person responsible for maintaining or planning the roads, this is invaluable information. The only way you got it before was to run a survey, ask 10,000 people, where do you live, where do you work, how do you get to work, and so on. You can now get it on a much larger scale in almost real time. Here's another bit of information from Marta's work. By analyzing which towers the phones are talking to, you can get a sense of people's daily commute patterns. And so she's taken 2 different cities, Chicago and Paris, and used the phone data to segregate how many people just stay at home during the day, how many people have a bipolar commute, how many people have a 3-way commute whereby they drop off the kid or whatever, and so on. And these are the relative numbers, and you can model the phone data and so on. So it's a way of looking, again, anonymously, but in great detail at how the city is functioning, in this case, how people move around. One more on mobility, and then we'll switch to something else. Taxis are a great fascination at CUSP. 2 of our faculty, Claudio Silva, who got his PhD here, I learned, and Juliana Ferrer, who also got her PhD here, got hold of 4 years worth of New York City taxi data. There are 13,000 yellow cabs in the city. They make on average 500,000 trips a day, so that's 180 million trips a year. And they've got 4 years of the data. What is the data? It's where each ride starts, GPS location, it stops, the time, the fare, the tip, the driver, the medallion number. You can go on and on. You can ask lots of interesting questions. Travel times, of course, but you can ask, does the tip depend upon whether the ride ends in a rich neighborhood or not? Or how do the tips depend upon the weather? Or how do the drivers reroute themselves when there's an accident? Things of that sort. This is the very simplest cut of the data. It just shows the number of trips per day in 2011 and 2012 throughout the 2 years. And you can see that there's a very regular weekly cycle. It's high on Friday and low on Sunday. And then for each of the years, you can see stuff happen. So this, for example, was Irene in 2011. This was Superstorm Sandy in 2012. You can see Christmas, New Year's, 4th of July is over here, and so on. This is one of what we like to call pulse of the city graphs. It shows the daily, or in this case, weekly variation of activity. You can drill down even further. They have segregated out here the 2 train stations, Penn and Grand Central, and the 2 airports, LaGuardia and JFK. And I've looked at 1 week in May, 3.5 million trips. And you see with 15-minute time resolution over the week, the number of trips out of the train stations, a pretty regular daily pattern, the number of trips out of the airports similarly, and then the number of tips out of the train station and the airports. More trips out of the train stations, more tips out of the airports. Presumably the cabbies know this instinctively or by experience, but it's really interesting to see it laid out like this. We can do some social science things. There are about 10,000 lottery outlets in New York City, and you can get pretty much 15-minute resolution on the lottery sales. And this shows the weekly pattern of lottery sales, 15-minute intervals. And this shows the geographical distribution of them. It's a startlingly regressive activity, as you might imagine. It's nice again to see it laid out. And then you can start to ask questions. Do the lottery sales depend upon the weather? Do they depend upon how well the sports teams are doing? Because people will feel more optimistic when the sports teams are winning, things of that sort. Okay, let me turn to a different way of looking at the city that we're exploring, I think pioneering, and it's inspired by this picture. This is a picture I pulled off the web. It's a thermal infrared picture of a New York City scene on a cold night. And the colors indicate heat now rather than light. And there are many interesting things in this picture if you look closely. For example, if you look at that building, I can read the thermostat setting in every apartment. I know, for example, that there's a data center in that building, and so I can understand why it's hot at the bottom, it's hot at the top where the vents are, and cool in the middle. And I know that those buildings are the Alfred E. Smith public housing buildings, and they're an embarrassment to the city because they're glowing red with the heat turned up and the windows open to keep everything comfortable. Interesting advantages in this, if you think about it for a minute. I got one camera that took this picture, but it's covering a large number of buildings, probably about 100 in this scene. It's persistent. I don't just get a snapshot as I would if I were in a satellite, but I get to sit and watch once every 10 seconds, every 20 seconds, and so on. It's granular. I can see information at the level of particular users' apartments. It's non-permissive. I don't need anybody's permission to do this. I don't need to go out and put a temperature sensor in somebody's apartment. Right? It's also cheap. I'll show you experiments we're doing with $1,000 cameras. And then finally, I have all this correlative data. If I can identify the buildings, I will know the demographics, the value of the building, et cetera, et cetera. I can use that to correlate with these observations. And of course, if you're a scientist, you will realize that you can do this in other modalities, not just the thermal infrared. Obviously, in the visible, I'll show you some hyperspectral data. You can imagine doing this with radio frequencies, LiDAR, and so on. Basically, doing from the tops of big buildings what you would do from a satellite, but a lot cheaper and with some advantages. So let me show you a little bit of that. This is the view from our office looking north. The Empire State Building is 3.8 miles away. And there are about 1,000 buildings in this scene. There are residential buildings in the lower half and mostly commercial buildings in the upper half. And this is the East River that separates Brooklyn from Manhattan. We live in Brooklyn, cusp. So the first thing to do is to demonstrate that we can understand what we're seeing. The city has a LiDAR topography data set. So it knows the elevation of the city's terrain with roughly 1 foot vertical and horizontal spacings. Right? And you can take that topography together with the image and do a little bit of geometry and basically identify every building in the scene. And these are the buildings that we see in this particular scene. It's a slice going north up the east side of Manhattan. And then we've just demonstrated we've color-coded all of the buildings by their distance just to demonstrate that we have that information. This is a similar color coding of the scene, but now by energy use intensity. The red ones are high energy buildings, the blue ones are cooler, and the high energy ones turn out to be hospitals. They use a lot of energy, as you might imagine. And we further demonstrated we know what we're doing by outlining in black every building that has an oil-fired boiler in it. So this takes the correlation of 4 or 5 different data sets in order to make such a picture and gain such an understanding. All right, so let me show you a little bit about the lights. I grew up, as Dennis mentioned, for 30 years I was at Caltech, which is a center of astronomy. Some people would say it's all astronomy and seismology. That's not true, but astronomy is certainly a major part of what goes on there. So I thought we would do some astronomy. I enticed a real astronomer, Greg Dobler, into doing this. So we took a camera on the roof. It's an 8.8 megapixel camera. We took one image every 10 seconds for about 2 weeks or 3 weeks. 1-inch focal length lens, about 4.5 terabytes of data we took raw. The immediate reaction everybody has is, well, what about privacy? We went first to the IRB, the Institutional Review Board at NYU, said we want to do this, basically take pictures of the lights, and they said, why are you bothering us? Everybody looks in everybody else's window in New York City anyway. What are you worried about? But in fact, we agreed that we would limit the number of pixels on the closest window, and the atmosphere turbulence nicely also blurs things out. So in fact, though that's the closest window or closest pair of windows in native resolution, and I like to joke that it looks like Z equal to 3 galaxies or something. You can't see much there, all right? Also, every analysis we do is aggregate and de-identified, so I'm going to show you some data on particular windows. I have no idea which windows those are in the scene. Here's a time lapse, let's see if it's going to work, of the scene through, I guess it's not working, too bad. Let's move on. I'm sorry I can't show you the time lapse. If you take one window and look at it like one star, you can look at its light curve. And this is the light curve for one window for one night going from 7 p.m. to 5 in the morning. And well, you know, you can see transitions in the intensity. Things happen. It looks like somebody turned off an interior light, perhaps. Somebody went to bed, looks like, big off. And then maybe the baby woke up or who knows what happened. Couldn't sleep, turned on the iPad or whatever. All right. So Greg, the astronomer, picked 4,200 windows out of the scene by hand. We now have an automatic way of doing it, and started to analyze the light curves in aggregate. Here's one example of that. We have about 3 weeks worth of data. The off transitions are on the top, night by night. The on transitions are on the bottom, night by night. And then you can start to play games. For example, we can look at a Monday night and order the windows simply by when it looks like they went to bed, what we call the big off transition. And here we go from 8 o'clock at night onward. Just the windows are sorted by when they turn off. You can then take the same sorting of windows but look at the Tuesday data, and they in fact get quite a bit scrambled. But then if you take the same Tuesday data but order it according to its natural ordering, you get very much the same pattern again back. And so it looks like in aggregate, the lighting patterns look very similar night to night, except on the weekends. But in microscopic, the people decorrelate after some time. You can see that a little bit more explicitly by looking at the correlation function of the windows. After 1 day, 2 days, 3 days, the windows tend to decorrelate with a width of a couple hours. The spike in the middle are the windows on timers, which go off at exactly the same time every night. Okay? So we can say that like 4% of the windows are on timers right now. All right, let me show you a different kind of information you can extract. If you look at the same thing during the daytime, this is 3 scenes taken no more than a minute apart. Let me go back. 11 o'clock to 11:01 in the morning. In the morning. This is the first scene, the second scene, the third scene, second, first. Let's see if the movie works here. No, it doesn't, unfortunately. Okay, it froze. So what you see if you look carefully, first, second, third, second, first, is a plume that comes out of this building when it fires up its boiler. There it is, you can see it quite clearly. First, second, third, second, first. So you can, let's see, how do we get to this? There it is. Again, I'm not sure the movie's going to work. That's too bad. If you look at the difference from one frame to the next, you can see quite clearly the plume coming out. All right? So we have suddenly now got a way of watching 800 buildings at once and learning who fires up their boiler, where did the stuff go, how much stuff was there, even the chemical composition at some point. So we think that's a useful thing environmentally. I'm going to skip this one since my animations, that one is working. We can do individual human experiments. We're doing that as well. You can just sit and watch an intersection outside of our building. The bus comes up and waits to turn left, and you can analyze his reaction time when the lights change. So this time-lapse difference shows both the lights changing and then the vehicles moving. You can do that for many changes of the light and measure the reaction time, and in fact see the reaction time go up as the level of distraction in the intersection goes up as well, which is what the psychologists would expect. Lots of other practical things we're doing for the city. I just list a few here. Economic map of the city. by combining census data, labor data, tax data, we can make a very high resolution economic map of the city. Bus driver optimization. The MTA has to call in extra bus drivers every day because people don't show up or they get sick. Can we optimize that so they don't call in too many and call in just enough? You can go on and on, the kinds of things that we're doing with the city. Okay, I'm going to talk a little bit about the science questions, and then I'll talk a little bit about CUSP itself. Can we document the pulse of the city in its various manifestations? I've shown you two already, the taxis on a weekly scale, the lights, electricity use more generally, on a daily scale. What's normal for these variables? How variable are they? What are correlations among them? How do they respond to perturbations? How predictable are events? Can we see precursors? So I think that's one. I'd call this sort of urban physiology. Another is, how do the macroscopic observables of the city, its morphology, its zoning, its patterns of movement arise from the microscopic decisions of people or institutions? There's the scaling of cities that the folks in Santa Fe, Jeff West among others, have come up with. How does that arise from the microscopics? What are the decision rules and agent-based models that would get you to the kind of morphology that we see? This is Paris, by the way, at night, seen by the lights from a satellite. Okay, let me talk a little bit about CUSP, and then I'll have a little more science to show you. CUSP started out as a partnership of universities, private sector, national laboratories, and city and state agencies. The universities, there are 6, NYU, Carnegie Mellon, Warwick, Toronto, Bombay, and City University. Among the industrial partners, IBM, Microsoft, Xerox, Lockheed Martin are the large ones. From them we get a little bit of cash, but more importantly we get data and we get people to work on projects. In particular, we're quite focused on energy as one of the things to try to understand. Con Ed and National Grid are very important partners in that regard. Con Ed supplying all the electricity, National Grid supplying some of the gas, Con Ed supplying the rest of the gas to New York City. When I came on board, I knew the talents and capabilities of the national laboratories, and we have involved 4 of them, including Brookhaven here on the island, Los Alamos, Sandia, and Livermore. Computational capability, sensor capability, and modeling capability is what we're looking for from the labs. And then I think uniquely and importantly, we're partnered with the city and state agencies concerned with New York City. 13 of the New York City agencies, ranging from environmental protection and housing, long-term planning and sustainability, all the way through to police and fire. And those folks, as well as the MTA, the Port Authority, give us data, give us problems to work on, and opportunities to demonstrate solutions. We run an educational program. There's a 1-year graduate master's program in applied urban science and informatics. It's a mix of about 30% informatics technologies, databases, GIS, visualization, sensors, machine learning, and so on. Another 30% about cities, and then about 30 or 40% in a big project that all the students execute. This is the first class that entered almost 2 years ago, a year and a half ago. We were 25, dropped down to 24 ultimately. Interestingly, they were out about 5 years on average. A third of that class was women. They came roughly half from abroad, and a third had, 28%, a quarter, had previous graduate degrees. The class this year has grown to 63, and we didn't get the mayor this year, right? We got the mayor that year, but the mayor was too busy this year. Anyway, what's interesting about them is that we're now up to about half women. This is a subject that really appeals because it's quantitative, it's data-driven, but at the same time has societal implications to it. And what's interesting in the current class is 6 of them are active New York City employees in finance. 1 is a cop, in the health department, and they bring a very different perspective to the classroom, as you might imagine. Oh, that was to highlight that. Where did they come from? It's interesting, again, we're trying to build, I like to say we go from censors to sociologists to civil servants. You know, about 40%, well, maybe 50, are what you would call classic science or engineering. About 22% social sciences, business, liberal arts, somebody from psychology, etc. Very interesting to get this group of students focused on cities as systems, as problems. Okay. Because I know a lot about the national labs, I figured that we had to have something to both induce faculty to work together and let them do things that they could not otherwise do as individuals. And so we're building some facilities, capabilities that are available for all of the researchers involved with the center. One is the data warehouse, which I'll say a few words about. A second is the quantified community, and the third is the urban observatory. The observatory, you probably have some idea already from what I've shown you with the lights. There's a little more to say about that. Let me show you about the data warehouse. What are the issues here? There are thousands of data sets about New York City. New York City government makes about 2,000 open data sets available on its website. The problem is that the data sets don't work together. They're not clean. They are not interoperable and so on. So you can't say, let's overlay income with energy use. It's not a simple thing to do. So we need to make them interoperable. Also, a number of those data sets are confidential, and so you need to worry about security. And clearly, as you start correlating data, you need to worry about privacy. So we're looking at a facility that will house all this data with multi-level security and privacy constraints. Here's the kind of data feeds that we have in principle and often in practice access to. This is DataBridge, which was a facility built by the last 4 years of the Bloomberg administration. It takes feeds from sanitation, health and mental hygiene, transportation, et cetera, et cetera. It's all in one place, but much of this data does not work together. Part of what we need to do is to make it useful and do interesting things with it. Privacy, as I mentioned, is a big deal. We sponsored a book last July, published on privacy and research and how you do this kind of work in a university setting. Julia Lane was the principal author. She is joining us actually in 2 weeks as a faculty member, but then there are a number of other lawyers, computer scientists, ethicists, all who have contributed to trying to figure out how we navigate the privacy story as we go into this kind of research. Quantified community is another facility that we are building. The vision here is just as neuroscientists take a square centimeter of cortex and want to instrument the heck out of it to understand how the brain works, why don't we take a slice of the city and instrument the heck out of it and see if we can understand how the city works. We call it quantified community. We are partnered with the Related companies, which is one of the big real estate developers in New York City. The target testbed is Hudson Yards, which is the largest real estate development going on in Manhattan right now, about 33rd Street and the West Side Highway. And the ambition is to take one or more of the buildings and fully instrument it. So questions, what do you want to measure? How are you going to measure it? How are you going to protect privacy and so on? You want to know about the buildings. How are they working? What resources are they consuming? You want to know about the infrastructure and the flow of materials. You want to know about safety and security. You want to know about the environment. And then finally, you want to know about the people. Convincing people to live here under this kind of instrumentation will be a challenge, but we think not impossible. You often get benefits from it. You've got to have the data secure, et cetera, et cetera. But we think you can learn a lot about cities by studying a slice in detail. Let me close with some other things we're doing with the observatory, some very recent things. I don't think I need to say much more about what the observatory is, other than to say that we're looking at multiple sites to cover more of the city and or covering the same scenes from different perspectives. Here's something that one can do that's kind of cute. That's a hyperspectral image of a scene with the Manhattan Bridge in it. So what do I mean by hyperspectral, for those of you who aren't scientists? Basically, it's a picture taken in 1,000 colors instead of just 3 colors. And so this is an instrument that spans from 0.4 to 1 micron, so it's the visible range that we see with our eye plus a little bit, and takes spectra in 1,000 different channels. And so here are characteristic spectra of different lighting technologies. High pressure sodium, there's an LED, fluorescent light looks like that, another fluorescent light, metal halide as used in automobile headlights and so on. And so you can take every light that you can see in this nighttime scene and characterize it according to the technology, the lighting technology that it uses. If you sit and now watch the buildings, you can tell when someone changes from an incandescent to a CFL or an LED, and then you can see if the lighting got more efficient, did they use more of it, which is a famous effect in economics called the rebound effect or Jevons effect. So we think that that's an interesting thing to look at. Here's another one, visiting physicist from WashU, Jonathan Katz, whom some of you may know. We set up a radio horn, an antenna, in one of our offices. It's got about a 15-degree wide beam, and it's looking at Midtown Manhattan, the Empire State Building. And we hooked up a receiver to it that measures just the total power in the cell phone downlink band. So I don't know the width of the band, it's probably 10 megahertz or something like that. And this is just a graph at, I think, 5-minute or even less 30-second intervals of the total power received by this antenna over about 10 days. And you see a very clear diurnal pattern, high during the week, low on the weekends. This was President's Day and so on. And so we think we have a very interesting way of measuring the total population or activity in an area without invading anybody's privacy, because this just counts the total number of phones that are there. We now need to get a much better antenna with better angular resolution, but it's not inconceivable to observe a large swath of the city and understand how people move around, useful for transportation planning, useful for emergency management situations. Let me close. The last set of data I want to talk about is an experiment that we did at the beginning of this month, the beginning of last month, April 6th to 15th. We partnered with the Aerospace Corporation, who build and operate a long-wave infrared hyperspectral imager, and I'll explain what that is in a minute. But we sat this instrument on the west side of Manhattan, going with a view, in Hoboken, looking at the west side of Manhattan from the Battery up to 59th Street. The instrument records in 128 different colors, or 28 spectral channels that run from 7.5 to 13.5 microns. For those of you who are not scientists, this spectral range is particularly interesting because every simple molecule has a different spectral pattern. And you can use this instrument, it was built to detect and identify plumes coming out of things on the ground. And so we're looking at several hundred buildings all at once, watching what they're emitting in almost real time. Here's first orientation of what we saw. This is a thermal infrared image, so no plume ID yet, but you can see Empire State Building and going north up to about 59th Street. The colors indicate the heat, roughly. For those, again, who are technical, it's the sum of all the spectral channels, so it's total infrared power. This is the same image taken about a minute later. And if you take the difference between them, you can see several things. First of all, you see that the images don't quite align, and that's because this is a mechanical scanning instrument, so it doesn't come back exactly the same place. Secondly, you can see stuff. There's a plume there, changed from 1 minute to the next. There's a plume over there, there's one over there, and then something happened over here that we don't quite understand what happened, but something. These data, as I said, are about 2-3 weeks old. And then you turn on the spectral analysis. So you have these 128 colors, you look at every pixel in the scene, and you try to match that color pattern to particular molecules. And we found, for example, ammonia coming out over there. We found difluoroethane, which is an ozone-friendly freon, coming out over there. We think the ammonia comes from cogeneration facilities that burn gas to spin a turbine commonly add ammonia to the exhaust in order to reduce the NOx. So we think that this is a way of understanding when people turn on their cogen facilities. Again, a couple hundred buildings in the scene, watching persistently. The difluoroethane, we have no idea where that came from. We did an experiment, a calibration experiment. I don't think I can show the movie because I don't think it works. But basically, we sent 3 graduate students out with cans of dust-off, which is difluoroethane, and they were on the waterfront in Manhattan, about 4,000 feet away, and you can just see 2 of them here right now. There's a third. If I were able to show you the movie, you see a big black cloud of this stuff identified spectrally drifting up the river. And so it's extraordinarily sensitive, right? One little can at a mile's distance you can see quite easily. We saw other stuff, CO2. You can see, we put the ID over there. You can see a plume of CO2 in emission coming out, and then you can color it in on the infrared image. What is this vertical line? There's a pole in the way, right, as the thing scans. This is real experimental physics. I mean, if I show you the setup, it would look familiar, like a laboratory with duct tape. We acquired 2,000 data cubes over the 10 days, and we're in the process of analyzing them to see what we found. One more thing which surprised us a little bit, we saw an awful lot of Freon 22, chlorodifluoromethane, right? This is an ozone eater, and these are taken at different times, but here it is over there. We see it both in absorption against the warm buildings, and we see it in emission against the cold sky, and these are taken at different times, and you see it coming out. In general, we don't know where this is coming from. It's supposed to be phased out over the next 5 years in the US, but somebody's emitting it in the city. Clearly, if I were the Department of Environmental Protection, this is an interesting tool, right? Given that we can identify every building in the scene. Okay, let me close up. As we build CUSP, what's success after 5 years? What are we trying to do? Figure out what this thing urban science is, or urban informatics. As you see, it's got physical components, it's got social components associated with it. What is it really? Is there a science here? Construct a center that's doing that, build some facilities, nucleate the kind of people that we need to study this thing, execute. I'd be content in 5 years with 3 or 4 projects that we can say simply and definitively, we made the city government better, or we made people's lives better in the city. I think we're on the road to that. I don't think we've quite done it yet. We're going to train several hundred people in this field, commercialize some technologies through our partners, and bring new tools to the social sciences, and then finally begin to franchise this globally. As you saw, we have some international partners. There is in the works a CUSP London, which will focus on health and well-being. And we think it's generally a pretty interesting subject to be having adventures in. So with that, thanks for your attention, and I'm happy to take some questions or comments.